sheet. I should have never. There should have been the flimsiest paper.
This looks. Yeah, this looks good.
Wait, do we have a 6.6?
Yeah.
And then we have a 6.6?
Which is why we're finishing 6.5 today, and then Monday and Tuesday is 6.6. I'll go ahead and give y'all the practice exam like on Monday, that copy, so you can be working on it.
Why?
Today? Possibly. Remind me at the end of class. Alright. So 6.5. 6.5 is where we have hit the unit circle, and because we are now in the unit circle, R is 1 the whole time, which means all of those formulas that we had with X, Y, and R have been adjusted to show that R is 1. So that's why now sine is the Y coordinate, X, cosine is the X coordinate, tangent's Y over X, and then you have your reciprocal functions that you would generate by creating the original list. Yesterday we learned it's really not. This was like 4 layers of steps that ends up creating the whole thing, and it's really not bad. I know it sounds terrible and it looks hideous. It's not. No. But I'll have to get with you. Yeah, you really do. You've been using half of it already. I'll get with you after that. Just try to stay with me, okay? But anyways, in a nutshell, this is the unit circle because the radius is 1 the whole way around. Because the radius is 1, we have those special right triangles in here. For instance, this is a 30-degree angle, and there's the right triangle. Look familiar? Okay, there's the 45-degree angle. There's the right triangle. With me? There's the 60-degree angle. There's the right triangle. Yes?
Yep.
Okay. In the 30, 60, 90, and the 45, 45, 90, do you remember those formulas we memorized? 1, 1, root 2. And then 1, 2, root 3. Okay? If I was to draw those right triangles like I just did and label 1, 1, root 2 or 1, 2, root 3 and find the sine, it would be the opposite over the hypotenuse, right? Or if I found the cosine, it would be adjacent over hypotenuse. Okay. All of that to say is where these numbers are coming from. These are the opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Okay? So that's where those numbers come from. And you'll notice that's why they look familiar, because they have either a 1, a 2, a root 2, or a root 3, because those are the only numbers we used with those special right triangles. Those are now the coordinate points of the 30-degree angle when drawn would have an x value of root 3 over 2 and a y value of 1/2. Okay? And so if I said, what is sine of 30? You would say sine, sine is y. Go to 30, it would be 1/2. If I said, what's the cosine of 240? You would go to 240. Cosine means the x coordinate, so it'd be negative 1/2. But we also are now into radians. That's the other thing. So we're not just doing degrees. We're now in radians. And that's where I'll have to show you. It's just a counting game. Okay? All right, so here is where we found those values, like what we just talked about, trying to catch her up. So like the cosine of 3 pi over 4, you would go to 3 pi over 4, you would write the x coordinate. The y sine of negative pi over 6, if you don't know where that is, you could add a coterminal 2 pi, and then 11 pi over 6 is on the unit circle. Sine means tell me the y coordinate. We practice this. Then we practice, what if they're ugly and they're not on the unit circle? You just type it in the calculator. None of these are on the unit circle. There's no pi over 7, definitely no decimals. There's no 2 pi over 5. So those are not on the unit circle, which means you have to use the calculator. All right, here's the new stuff. We're looking at the graphs of sine and cosine. For the graph of trig functions, we're going to let x be the angle measurement. And then we're going to look at if you were to plot a point every time you found the x-coordinate, what would it look like if you connected the points, okay? So this is what we've already put together. It's only part of it labeled. It doesn't have all of them. Then you go to this slide, and you're going to see where I've got a blank table and then a blank graph. And this one is the sine function. This one is the cosine function, okay? Those are the easier ones to work with. Tangent is totally different, which is why it gets its own slide. First, let's talk about what looks different here. Do you notice how the x-axis is now, instead of regular numbers, it's the radian measures? You see that? Well, if we go back over here to this slide, it said we're going to let the x-axis be the angle measurement. And we're in radians, right? We're not in degrees. We've leveled up. So we're talking about the radian measure. Okay. So it looks very intimidating. It's really not bad. The other thing is, what we're fixing to do is graph these two functions by hand. And because this is where My Math Lab, you should appreciate it. You actually don't have to graph by hand because My Math Lab has the widget. You just have to push the correct button. So you're welcome, because when I used to teach this without My Math Lab, they had to graph everything by hand. Like the test was a blank chart, and they had to graph it by hand. There's a pattern though. So while this looks really intimidating, you're going to notice that there's a pattern. So you're really not generating the whole graph. You're generating the pattern, and then you're just repeating it. All right? Now, it goes back to exactly what we did right here. Everybody with me? If I said, let's see, we're graphing sine first. If I said, tell me sine of 11 pi over 6, you would go to your blue formula sheet, and you would tell me the y-coordinate of 11 pi over 6, and what do you get? Negative 1/2. That is what we're going to do here, but now we're going to plot 11 pi over 6 as our right or left, and then negative 1/2 would mean I'd go down half. You hear me? So that's what we're going to do. See it now? All right, so keep your little blue paper out. It's going to help. Sine means look at which one? Y. We're just looking at the y. This is why sine and cosine are easier, because you're just looking at y or x alone. 0. 0 pi. Now, you can look at your blue chart, but I'd love for you on those nice easy ones to visualize it. So 0 pi is over here, right? It's 1, 0. What's the y-coordinate? 0. Plot it. 0, 0. Pi over 6. Now, in this case, quadrantals, visualize it, then confirm it with your blue paper. These other ones, feel free to look at your blue paper. Find pi over 6. Tell me the y-coordinate. 1/2. We're going to write decimal because we don't have a lot of room. So I'm going to write decimal, 1/2. Now question, do you see pi over 6 over here? No, so we're not going to plot that one. It's not on there. You with me? We're only going to plot the quarters, increments of 1/4. Okay, pi over 4. Look at your blue sheet. What's the y? Very good. And like I said, we need decimals so we can plot this crap. I have no clue where square root of 2 over 2 is. So go to your calculator, and I want you to type square root of 2 divided by 2. And we're going to go to the nearest 10.
Thank you. I don't think I've used my personal calculator.
It's very good. the chai, I need to ask her if she puts cinnamon, because I'm not a real big cinnamon drinker fan, but it's very good.
Whoa, why is this orange?
Does the top say test mode? You're fine. It's been that way
The back
since.
of it also says it's Holcombe.
That's fine. That's where someone borrowed it. The only way to get it out of test mode is to hook it to a computer and then go to the software program and reprogram. I'm not doing that.
That sounds like fun.
Why does it do?
I have no clue. It's been that way since.
I really forgot the window was open.
Huh?
I feel the air coming in.
Yeah. It was just stuffy from the first one. What'd you get? Root
0.7.
Yeah, 0.7. Now this we're going to graph. That's an increment of that's a quarter, right? So we're going to go to pi over 4. You can see if I go all the way up to 1, that would be 1. Well, it's 0.7, so I'm going to back down just a little and put a point. All right, pi over 3. Get the y value. What is it?
The screw root of 3 over 2.
Now type it in because I can't graph that. 0.9. So we're going to go almost to 1, right? We're going to get closer. No, wait, pi over 3 is not on here. So
Oh my.
we still need the t-table. We're just not plotting it. Plotting the increments of 1.
I plotted it on the second.
We'll erase it.
I didn't.
You need pencil. But it's okay because the next one is going to be 1, so just make it a bigger.
Math class.
I always use pen when I'm taking notes.
Pi over 2. Okay, visualize it. So that's 90.
That's different.
So that's the coordinate point 0, 1. And we want the y value, so 1. So pi over 2 is 1. So see, you can save it. Now keep going. 3 pi over 4. Get the y coordinate. Go to the nearest 10. Okay, and we said that was 0.7, I think.
Yeah.
3 pi over 4 is an increment of 1/4, so we're going to plot that. So pi is 180, so that's 0. No, that's negative 1, 0. So the y value is 0. Five pi over 4. Find the y value. It's a radical, so you're going to have to type it in. It is negative 0.7. You should see a pattern.
It's just going to be negative 0.9.
Wait a minute, hold on. 5 pi over 4, negative 0.7, so we'll put that right there. 3 pi over 2. No, I think 3 pi over 2 is a quadrantal, which if it's quadrantal, that means it's either 0, 1, or negative 1. And it's negative 1.
I'm just going to negative 7. Or negative 0.
Negative 0.7.
Sorry.
You're good. That might be cookies.
I brought my name today.
Do y'all want
I
cookies?
do.
We do have some people interested.
Oh, you gotta get.
I was like, man, that's not
I was like, dang it.
She's gonna lick your cookie and then hand it
I
to
already
you.
had a cookie.
Oh, I thought you were getting some.
What is that?
Oh.
How many?
You are getting
82.
Yesterday she wore
Yeah.
socks.
Had a restart.
Out of the socks. Like it was popping out. Today?
Restart.
Adrena. Adrena. We're playing World Cup. Huh? Did she say we're playing World Cup today? Did she say that?
She talked about it yesterday.
Probably because she wanted to last Friday, and then no one wanted to go to practice.
Okay, do you notice, thank y'all. Do you notice that it's a nice smooth like S curve? And what do you think would happen if I kept going?
It would keep doing the S curve.
Yeah. So this is leading us to a vocab word that is 3 slides away. So I'm going to go ahead and tell you the vocab word because now you can see it. The vocab word to describe on a trig graph the length of the graph where the pattern makes one complete cycle, I guess you could say, before it starts repeating, right? Like nothing up here is repetitive, but if I kept going, now I'm repeating. You can see the pattern would start repeating. Okay, so the vocab word to describe how long did the graph run to complete one cycle of its pattern? It ran 2 pi, and the vocab word is period. The period of sine in its mother function form is 2 pi. It takes 2 pi, from 0 to 2 pi, for the curve to do one full cycle before it starts repeating. Okay? So that vocab word comes up in 3 slides. And what you're going to start doing is you're going to start recognizing the period length of the trig function. And it means how long the curve stretches to run its cycle once. Okay? All right. Now, let's finish this though. If you have a highlighter, it might be helpful to highlight okay, 2 things. You can either highlight the curve itself, or let me show you an alternative thing. Let's finish the curve. So let's backtrack it. So it would be coming down a little bit, all the way, a little bit, 0, a little bit, all the way, a little bit, 0. Finish the curve. What? I just went in reverse. So this was coming down. So I knew go a little bit, all the way. A little bit, all the way. That's the. Oh, okay. So for this one, let's highlight. You're going to hear me call them anchor points. Okay. What we're going to end up doing is we're going to memorize, well, not memorize, okay. You're going to be able to generate the anchor points for sine and cosine graphs. And the way you generate the anchor points is literally thinking in your head, what is the y value, watch my arms, what's the y value at 0 pi, 0 pi? The y value is 0, right? Yes? Okay, what's the y value at, you could do pi over 4, which you know is root 2 over 2, which is approximately, we said, 0.7. What's the y value at 90? 1. What's the y value at 180? 0. What's the y value at 270? Negative 1. What's the y value at 360? 0. So those are your quadrantal anchor points. I'm going to call them just your anchor points in general. Let's highlight them. Ooh. So 0 is an anchor point, pi over 2, pi, and then 3 pi over 2 and 2 pi. Those are your anchor points because those are the quadrantal radian angles. Now, what I would love to see if you can do is repeat the exact same process, but now you're looking at what coordinate? X. So come down here, and now I want you to make the T-chart of the X coordinates of all those exact same radian measures. Alright, what is the x coordinate at 0?
That is a W.
What's the x coordinate at 0?
1. 1.
Oh.
1.
Right. What is the decimal at pi over 6? You end up with like root 3 over 2, which is 0.9. Loosh. Pi over 4. You get root 2 over 2, which is 0.7. Pi over 3 is 1/2. The x coordinate at pi over 2, so that's up here. The x coordinate would be 0. 3 pi over 4 is negative root 2 over 2. Pi is 180, so the x coordinate would be negative 1. 5 pi over 4, it has a 4 in the bottom, that means it's a root 2 over 2. But 5 pi over 4 is in quadrant 3, so it's negative 0.7. 3 pi over 2 is 270. What's the x coordinate? 0. 7 pi over 4 is root 2 over 2, right? And then 2 pi. 1. So to plot these, you're only plotting the ones with 4 or 2 in the denominator, because that means increments of 1/4. Or your nice whole ones, your quadrantal angles. So 0, 1. Not pi over 6. All right, pi over 4, 0.7, so it means close to 1. Can't graph pi over 3. Pi over 2, 0. 3 pi over 4, negative 0.7. Pi, negative 1. 5 pi over 4, negative 0.7. 3 pi over 2, 7 pi over 4, and 2 pi. Did you get it?
No, I have not had it. My pi was a 1 instead of negative. So it would have been a W.
If I was to keep going, you can see where now I would basically be picking up this from this pattern over here. It would keep going. Now let's finish the rest of it in reverse. Reverse. So almost, all the way, almost, all the way. Okay, just like in the last graph, we highlighted our quadrantal point values because those are going to be our anchor points. We're going to do the same thing here. Your quadrantal radian measures, you should start knowing these by heart. You've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. The purpose of that is if I say, I need you to sketch the graph of sine or cosine, or if I say I need you to sketch it and then I need you to shift it, you've got to have your anchor points, your mother function first, and then you can know how to move it. You don't have to have all of these points to generate the sine and cosine graphs. All you need is the highlighted anchor points, and then you can see the graph. Okay? What do you notice is the biggest difference between sine and cosine graphs? Because they look like the same curve, and they are. Looks like it's just shifted, right? The anchor point for 0 pi, The anchor point for 0 pi is the one that I memorize to know the difference between when I'm looking at a sine or cosine. If you notice, and I'm going to highlight it in a different color, you can either highlight it in a different color or you can maybe just make it a bigger point, whatever you want to do. So this anchor point that kind of starts the pattern is here. This anchor point that starts the pattern is there. What do you notice about the difference between them? Bam. Sine starts at 0, cosine starts up at 1. Okay? If you can memorize that, that sine starts at 0 and cosine starts at 1, then you can generate cosine's up here, so it's going to do like that. This is cosine. Sine's here, so it's going to do like that. This is sine. You see what I did there? I generated the graphs like a sketch of it by just using the anchor point, that first one for 0 pi. Right? Y'all with me? Now, I'm not asking you to necessarily remember sine of 0 is 0, cosine of 0 is 1. There's two ways to remember this, or muscle memory. One way is to know sine means tell me the y value at 0. That would be over here. So the y value would be 0. So one way is to just generate it, like answer the question. Tell me the x value at 0. Well, that would be 1. That's one way to do it. Or cosine, don't know why. I always think of a roller coaster, and the best part of a roller coaster is when you're already at the top and it's going to shoot down. So I think cosine, like a roller coaster, where does a roller coaster start its initial journey? It starts up high, right? It's got to get up to that highest point before it can take off. So I always memorize it that the roller coaster, the cosine, starts up at 1, and then I know sine starts at 0. But I could answer the question too. It's just that's what I use to get there faster. Okay. Yeah. Now, having said, well, you can wait for you. We're doing the tangent. Catch you up. Okay. All right. Look at this. No, good. So look at this one.
I say we wait, because this is going to be a lot.
You're watching film.
I'm watching you. Phil's on the background. My camera's right back. For the 7th time we do
This is tangent, okay? What makes tangent uncomfortable is two things. One, the graph looks totally different. Looks totally different than sine and cosine. Which is good though, because if you ever have the graph that is going to do what this, like tangent does this. So it's totally different. So that's good because that means you can't miss it. Like you can't mess up tangent, right? You cannot look at these graphs and say, oh, I think that's tangent. Because then I'm going to be like, you didn't listen. There's no way. That's sine, cosine. So the good news about tangent is it's so different, you cannot mistake it. You know when you're dealing with tangent. What's uncomfortable with tangent is you cannot just look at the y, look at the x. You have to now actually divide y over x. That's the annoying part of tangent, okay? We actually will not work with tangent a lot because sine and cosine is more interesting. So we're going to basically look at it, talk about it. It'll come up maybe a couple times, but our real focus is sine and cosine. So this is why tangent is uncomfortable, because tangent is actually computing y over x of these values. Now, let's go to your blue paper, find 0 pi. If we do y over x for 0, first of all, what is the coordinate point? Might help to write it over here. It's 1, 0, correct? So y over 0 would be sorry, y over x would be 0 over 1. Well, 0 in any fraction, like on top, when 0's on top, it's okay, and the answer is 0. Now, pi over 6. If you go to your pi over 6 on your blue chart, what are the coordinate points of pi over 6? Someone tell me.
Square root of 3 over 2 and 1/2.
Okay, I'm going to write it right here because it's the coordinate points for pi over 6. But we are not going to worry about when it's those coordinate points because, one, it would be getting into the details when you really could just focus on the nice, pretty answers and you can still get the curve. We don't need that ugly decimal that's going to come up here. Technically, you go to your calculator, you do 1/2 divided by root 3 over 2. We are going to skip it because it will fall into play when I draw the graph, okay? Let's go to pi over 4. The increments of 1/4 are nice because what do you notice about the x and the y every time? They're the same value. You just have to watch your signs, right? So if you go to pi over 4, it's the same coordinate. So if I divide them in any order, I get, what? 1. Now if you go to pi over 3, you get that hot mess again, right? So we're going to skip pi over 3. Now go to pi over 2. That is the coordinate point 0, 1. If I do y over x, what do I get? I get undefined. That means we have an asymptote, which is why tangent is not as fun because there's asymptotes involved. You know, nothing's fun when an asymptote comes into the picture.
What's that use?
3 pi over 4, that's an increment of 1/4. That means that the x and y values match. We just have to watch our signs.
-1.
You get -1. Pi is out there at 180, so that's -1, 0. So if I divide y over x, what do I get?
0.
I get 0. Right?
Yep.
I have to think about it. 5 pi over 4, x and y are going to match. You're in quadrant 3, which means you get +1, right? Because they're both negative. All right, 3 pi over 2 is a quadrantal angle. It's 0, -1. If I do y over x, what do I get? I get undefined. Another asymptote. You know, because usually where there's one asymptote, the second one, I'll quit. All right, 7 pi over 4, that's a 1/4 increment, which means they're going to match, but it's quadrant 4, so it's -1. Then 2 pi is 1, 0. Y over x would be 0. Now you can see why we didn't really need those two ugly ones where it was going to be an ugly decimal. We don't need them. We're going to be able to graph it from this stuff right here. I like to go in and put my asymptote first, so that way I don't accidentally plot something there. So pi over 2, we're going to drop an asymptote. 3 pi over 2, drop another one. If you think about pi over 2 and 3 pi over 2, where are they on the unit circle? Put both your index fingers on, put one on pi over 2 and put one on 3 pi over 2. Where are they? Where do you notice? They're like on the y-axis, right? So every time if you were to keep going around and around, like adding 2 pi and finding more values, every time you hit the y-axis, you hit an asymptote. Every time. And that's because now 0's in the bottom of the fraction for tangent, and that's a no-go. All right. We got 0, 0. What makes tangent a little weird is we're facing a graph. well, let me graph it and then you'll see. All right, we got pi over 4 is 1. We have pi over 2 as an asymptote. 3 pi over 4 is negative 1. Pi is 0. 5 pi over 4 is 1. 7 pi over 4 is negative 1. 2 pi is 0. So what makes tangent weird when you go to graph it, like using the same, the radian measures within 0 to 2 pi, you end up graphing basically 3 tangent curves. There's 3 here. There's half on the left, there's a complete one in the middle, and then there's half on the right. So that's why it's kind of weird. If you look at the graph, you can kind of see the pattern here. So basically it's 1, 0, negative 1, asymptote. Asymptotes on every pi over 2. Then we got 1, 0, negative 1, asymptote. 1, 0, and keep going. Now, your anchor dots are really just the ones that graphed completely, and you can graph either the whole, like you could do the whole thing if you wanted to, or you can do the anchor dots, which is these 3. And then you would need to know that you do have asymptotes on the pi over 2 increments. But like I said, we are going to be manipulating sine and cosine. We're not going to manipulate tangent. It's not as interesting. And that's because, like, the curve is only right here to here, and then the curve repeats, whereas sine and cosine, since it goes out horizontally, it's a more interesting graph as you change it. All right, we graphed sine, cosine, tangent. Go to the next slide.
This is more graphic.
This is just reading the graphs.
Are we reading the graphs with 3 sides?
No. All right, so something that you may remember, I'm sure, from college algebra, domain and range. Domain and range, we're in terms of sine and cosine, because again, those are the more interesting graphs. If you look at it, you know that they definitely keep going, right? They go out in a horizontal fashion. Now, range, so you'll notice it says the domain of sine and cosine is all real numbers. That's because it just keeps going. Shouldn't have a problem there. Range, you have to turn your head sideways. Remember we talked about this. And you're saying to yourself, like, what is it covering on the y-axis? It's oscillating between -1 to 1. So the range of sine and cosine is -1 to 1. Okay. Read that, like, put it in your pipe and smoke it. I guess you could say, digest it, and then now let's move on.
So no matter what, the range will always be -1, 1.
Well, of the mother functions, If we turn the volume up, right? If I turn the volume up, the amps get more. So then the range changes.
But
the mother function is going to oscillate between -1 to 1. Okay. Now, this slide's important. Here's those vocab words that I said were coming down the pipes. I said in 3
periodic
slides. Not periodic. Well, it is periodic, but it's not like the periodic table. It's not the same. All right, take your highlighter. A function is said to be periodic if there exists basically a pattern. Okay, like there's a pattern that it repeats. Now, the actual college math behind it is this equation right here. We are going to replace S with theta. If you don't mind, replace S with theta. It makes it a lot easier to understand. S is referring to that arc length, which is hard for people to remember. But theta, everyone knows that that is referring to the rotation, right? So right here, so it's periodic because once it makes it to 2 pi, it's going to repeat, right? It's hitting those coterminal angles, which is why there's a pattern that repeats itself, which is why it's called periodic, because it has a certain pattern, almost like a stamp, that then now you just repeat it over and over and over once you find like the initial pattern. Here's what you need to highlight. You need to highlight amplitude. And where is it? Oh, right here. Period. I don't want to highlight periodic because periodic is like a word to say, oh yeah, that picture, that graph is periodic. Great. Period is the actual, like, a math value. What's the period of sine and cosine? It's 2 pi. It takes 2 pi for the graph to generate one complete cycle. Okay? Take your highlighter, highlight that period is referring to how far it stretches across to do the one cycle, and then I want you to highlight amplitude and highlight these little arrows right here and here to show you that amplitude is referring to the height of the curve. Amplitude of a periodic function is half, right? It's half the distance between its max and min. It is always positive. Always positive. Amplitude's always positive, right? Oh, yeah. What is that? I forgot. 240. Okay. So we got amplitude. Now you can remember that it's half. I personally don't want to remember that. I like to do this. I basically say to myself, "Where's my midline?" This is the midline. Midline is like the middle of the curve, right? And then I ask myself, what's the space, the distance from the top of the curve to my midline? Because then that takes care of the whole half thing. Because that should be duplicated, like, you see what I mean? Instead of saying, oh, it's 2 divided by 2, which is 1, I just like to say, where's my midline? Okay, it's 1. So you can do that either way. How are you going to remember which one's which? Amplitude, I want you to think of sound waves. If you turn the volume up, turn up the amps, right? You get like an amplifier in your car. The sound is louder, right? So think of turning up, like if I'm changing the amplitude, the curve would get more active. Or if I'm turning it down, then the curve would not be as active as all. Period, it's almost like thinking as an accordion, basically. You're saying like, how stretched out is that one pattern to complete on the graph? And in the mother function, it's 2 pi. Now sometimes we're going to adjust it by doing, here's those words, horizontal shrink. And then it's going to be really active. Sometimes we're going to stretch it into a horizontal stretch, and then it's going to take forever to complete the cycle. Okay? All right. Look at this slide right here. This slide is showing you the pattern, the fact that, if you're doing sine up here, you've got the same value as if you had done a negative angle rotation, but it would land down here in the negative spot. They're showing you that there's a symmetry. This doesn't come up a lot, but it is important. I put it on here because we might talk about it like a once or twice. But do you remember these words, even and odd, from
Yeah.
college algebra? The sine
Right.
function is odd origin, because it's symmetrical by a 180-degree rotation over the origin. Remember that odd starts with O and origin starts with O. You rotate, O. You rotate 180. You turn your paper upside down and it will be the same graph. Even means that it's symmetrical across the y-axis. It's symmetrical across the y-axis, which means if you take the paper and you fold the left to the right, they match. All right, stay with me. We don't have much left. There's no practice problems. It's just talking. It's me talking, so please listen. This is really important. Yes. This slide right here is really important. These are the mother functions. Remember me saying we're only going to deal with sine, cosine. Those are the ones that are interesting. This is the chart to tell you the properties of the mother functions for sine and cosine. There's the graph. We already graphed it. Continuous just means you never have to pick your pencil up to trace it. Right? The period, we've already said, it takes one full rotation to generate the sine graph in its first pattern. Domain, we've already said it's all real numbers because it keeps going horizontally. Range, we've already said it oscillates between -1 to 1. Amplitude, we've already looked at it. Y'all know me. I find the midline, and then I just say how high is the curve to the midline, and I can see that it's 1. It's 1. And then it is an odd function because if you take your paper, look at that graph of sine. Now turn your paper upside down and it's the exact same graph. So it's considered odd. And I guess that would mean because if someone was in class and they took their paper and turned it upside down, you would probably think they're an odd person, right? Or that's an odd behavior. Okay, cosine has pretty much the exact same properties except it is even. If you take your paper and turn cosine upside down, you get a totally different graph. But if you take your paper and you fold left to right, you have the symmetrical picture across the y-axis. Okay? All right. Why have we not talked about tangent? Well, that's because tangent's boring. Tangent's annoying. So tangent comes from y over x, right? We already said that. Well, where was the tangent function undefined? What did we say? It was always the
Over 2.
We said it's the pi over 2 increments, right? It's where theta is, it could be positive or negative pi over 2, right? You could go negative. You got negative pi over 2, or we said it was 3 pi over 2. And then it kept going. You could keep rotating, right? All right. Now, go back to your T chart from the other slide. Where was tangent equal to 0? What values?
Pi,
Yeah.
2 pi,
0 or negative, right? You could go in reverse. Tangent is 0 on what? X-axis. So increments of pi or 2 pi, or you could keep going. Where was tangent 1? This is us just showing the pattern. Where was tangent 1? -7, what was it? -7 pi over 4. So we don't really have a nice pattern here. So I'm going to put, like, there's some stuff before it probably. You got -7 pi over 4. What else?
-3 pi over 4.
-3 pi over 4. What else? Pi over 4. And it would keep going, right? Where was tangent -1?
-9 pi.
-9 pi over 4. What else?
-5 pi over 4.
Okay. What else?
-pi over 4.
Okay.
3 pi over 4.
And it would keep going, right? This is just summing up that tangent is not as interesting because you've got 1, the asymptotes, 2, you've got the numbers 0 and 1, which are easier to graph, but you basically only have nice numbers 3 times on a tangent curve. The rest are those hideous decimals. Whereas your sine and cosine functions, your nice numbers happen more often. We have more anchor points. All right. If you look at this slide right here, it is summing up where we said that tangent is undefined, which meant that y over x ended up being 0 on the bottom. Like something was here.
That's not it.
Huh?
I saw it.
You had the y coordinate and then x is 0. Wherever x is 0, you end up with an asymptote. And that's because of the tangent function. Where's tangent 1, 0, and -1? That's where you can see those are the curves we already graphed. Like there's the tangent function right there. Right? Now, if you were to try and talk about the domain and range of tangent, so it's a little backwards. This time, the domain has restrictions because we're jumping on these asymptotes, but the range, turn your head sideways, it's covering the entire y-axis. So the range is the easier question to answer. It's going to cover everything. The domain would be the increments on those pi over 2 values, which we've already talked about. It's every pi over 2. Up here, down here. Up here, down here. Every time. Over and over and over. So the range would be all real numbers, except it's going to skip. This is the y-axis, if you think about it. It's going to skip on the y-axis every time it hits. Now, this next slide that I'm going to show you is a one and done. We're going to look at it, we're going to talk about it, and then it won't come up again. This slide is showing you the co-function graphs, which you can see is like, the co-function, like the reciprocal of sine, is in red. The reciprocal of cosine is in red. The reciprocal of tangent, which actually is not as bad, is in red. So we won't be manipulating the reciprocal graphs, but I wanted you to see that if you were to graph them, this is the hot mess that you would end up with. Bless you.
Thank you.
And then this last slide here is putting everything we talked about on one slide. Huh?
We ended up along.
Oh, well, good deal. What do I have after it? Question 1. That's comforting. The first question. Find the coordinates. Oh, I remember now why I put this on here. People were freaking out about this question. This is saying, do you know where to put a negative when you change quadrants? If they give you a point and now they say, oh, by the way, you're going over the x-axis, or you're going over the y-axis. You're just putting the negative where it goes. Right. So, number 1, Don't overthink it. And plot the point. This is positive, positive, so that means this is in quadrant 1. Then if you reflect it over the x-axis, it would land down here. So y is negative, see what I mean? That's why that was